Good afternoon. Welcome to this webinar. My name is Robert Grace, Editorial Director of the Plastics News Global Group. Today we're pleased to have an expert to discuss plasma surface modification. But first, a few housekeeping tips. You may listen to the presentation's audio through your computer speakers or by telephone. The phone number and access code are on your screen. To optimize your view, minimize the box on the right by using the button at the top of the box. If you have a question, open the box on the right and type it in. We will answer questions after the presentation. The presenter's slides, as well as the archived version of the entire presentation, will be available in about 24 hours on our website at www.plasticsnews.com/webinars. We want to thank the sponsor of today's webinar, Enercon Industries Corporation. Enercon is a leading global manufacturer of corona, flame, and atmospheric plasma surface treating systems. Companies in the printing, coating, laminating, and extruding industries rely on Enercon to provide surface treating solutions that functionalize the surfaces of a variety of materials. The company's product line features atmospheric plasma discharge systems specifically engineered to meet the unique application requirements of webs, sheets, and dimensional objects. Each of their technologies is available for comparative testing in their surface treating laboratories in Menomonee Falls, Wisconsin. And finally, I want to point out that the content of today's webinar is supplied by Enercon. Surface treating is becoming more important, and technology has expanded substantially in the last decade. For example, variable chemistry plasma systems go beyond basic improvements in surface energy. These systems can now clean, etch, and functionalize surfaces for a variety of critical applications. The technology is application-driven as the industry looks for more efficient and faster production methods of bonding inks, adhesives, paints, coatings, and other surfaces. Today, we have Rory Wolf, Technology Manager for Atmospheric Plasma Systems, to bring us up to date on surface modification technology. Rory is certainly qualified to speak on this topic. In fact, he wrote the recently published book titled Plastic Surface Modification, Surface Treatment and Adhesion. Rory has nearly 30 years of experience in the plastics and paper industries. And now, Rory, we'll hand it over to you.
Well, thank you very much. Enercon is pleased to be here and to represent the presentation that we've just discussed and to bring you more information on how we can advance together adhesion for plastics. Enercon has been providing this type of technology for the last 35 years, and at this point we understand the marketplace is looking for, as we say on screen here, smarter, faster, better, greener technologies that meet the needs of the changing plastics environment. So we're very pleased to be with you today, and again, thank you for your attendance. Our topic today will be plasma surface modification, improving adhesion with inline plasma treatment. We'll be talking about specific types of technologies, but to preface the discussion, we want to ground everybody on the topics of surface energy and the functionalization of polymers. We want to ground you in understanding the reaction mechanisms that are used to prevent any type of lack of adhesion to any type of surface. We want to give you information on how we change polymer surfaces relative to promoting adhesion, give you information on how you can specifically functionalize materials, and specifically we're going to use polypropylene as our standard for that discussion. We're going to talk about the different types of atmospheric-based plasmas for polymer surface modification, primarily because inline continuous methods are the method of choice among many, if not all, of our customers relative to the use of promotions relative to adhesion. And then in the end, we're going to talk to you a little bit about some specific types of materials and recommendations relative to treatment of those materials. So without further ado, I'm going to move forward with the discussion. We'll start with talking about surface energy and how we functionalize materials. Admittedly, most of you will realize that most polymer materials are hydrophobic and as such require some type of modification. There are many types of modification out there, but whatever method you use, you have to be able to ensure that the surface energy of the base material has a surface energy that is 10 millinewtons per meter or approximately 10 dynes per centimeter higher than the interfacial solution that will be applied to that surface. To demonstrate this, we've got two graphs, one of which identifies the different types of mainstream polymers that are used in the plastics industry, primarily in the three-dimensional and film-based industry, and surface tension relative to the liquids that are applied to those surfaces. If we focus specifically on polypropylene, for instance, which has a native surface tension of about 29 to 30 dynes per centimeter or millinewtons per meter, and we look at the surface tension of solvent-based inks, which usually have a surface energy of about 36 to 37 dynes per centimeter, you can see that that existing surface energy level for polypropylene is inappropriate to at least create a base level of adhesion. And so it's necessary to raise that surface energy to approximately, again, that 10 millinewton per meter benchmark or incremental increase in order to achieve a satisfactory level of adhesion with solvent-based inks. If we look at the more solids content inks, such as UVs and water-based inks, that have very high surface energies, polypropylene must be raised to even higher levels in order to be able to achieve adhesion. And so it's a two-factor equation. One, the surface energy of the base material. Second, the surface energy of the adherent that is going to be critical to create the right adhesion level. One of the first methods and one of the more inexpensive methods of creating this type of adhesion are air plasmas. Air plasmas rely on the discharge of energy from an electrode that will create a change in the surface of any type of material. It does so by initially avalanching some micro discharges through channels, what are known as channels. The duration of those discharges or micro discharges are about 10 nanoseconds. They have a diameter of 10 to 100 microns. We realize that, and you may realize as well, that the temperature of these micro discharges are quite high, usually a few thousand degrees centigrade. But when you discharge these electrons through these canals and they make their mark relative to the surface of the material, the change in the surface of that material temperature-wise is only slightly higher than ambient. The density of these particular type of micro discharges is about 10 millijoules per cubic centimeter. Harnessing this type of an air plasma can take place in various different methods. The top indication is a reflection of a planar approach whereby we are using high voltage between 8 to 20 kilovolts, building up current voltage in that anode or top electrode until the point where we are able to create an avalanche of electrons to the surface of the material to a ground plane. What is interesting about the profile of that discharge is, as you see it, those micro discharges will actually arc to the same spot on the ground plane over time. And this is a memory effect. There's a lot of detail behind this, but essentially those discharges are random, but at the same time will be in place relative to their discharge path to the cathode. It is nonetheless a high voltage arc. It is ionizing air as the medium between the anode and the cathode, or the electrode and the ground plane. When that air is ionized, we have electrons ultimately bombarding or colliding with the surface. In this case, a polymer surface breaks the existing bonds on that surface. It creates a free radical effect, which allows the reactive oxygen species that come from the ionization of the air to form polarity at the surface of the material. You can see by the various inset pictures that we've got different ways of delivering that discharge to surfaces. They can either be, again, arcs from an anode and a cathode, a blown arc from an electrode and a ground electrode, as well as a blown ion nozzle type delivery method. Talk a little bit about flame technology. Flame technology has evolved over time and has become a much more useful and much more controlled process with regard to both three-dimensional objects as well as planar and roll-to-roll materials. It is a gas mixture typically of methane gas and air. The combination or the stoichiometric ratio is usually about 10 parts air to 1 part gas. The gas, again, can be methane or natural gas. It can also be a butane or propane. If it is the latter of the two, it is typically then a change in the air component by a factor of 2 or 3 to ultimately completely combust the specific type of hydrocarbon gas that's being used. After that treatment, however, you are getting a carbon-based functionality, typically hydroxyl groups, carbonyl, and carboxyl groups. When you treat a surface by flame, you are ultimately oxidizing the material. At the same time, there is a small amount of low molecular weight organic materials or modules or glodules of these different types of depositions that will occur along with the oxidation on the surface of the material. It is a high velocity discharge, so the impact of the species of the surface will create chain scission at the surface of the polymer and create these small modules or topographical mounds that are at the surface of the material. And yet, as a result of that discharge, we get not only a grafting of carbon-based groups, but we're also getting longevity of treatment, and you get the functionality that you're desiring with that treatment. The third type of technology that harnesses plasmas is variable chemistry plasma. This technology, again, can be applied to three-dimensional objects, roll-to-roll materials, and sheet materials. But it's a gas-phase plasma technology that allows you to utilize different types of gases to create a specific type of or prescribed surface effect. We are using gases typically with discharges at low temperature, low voltage, and high frequency. The principle is similar to the flame plasma and air plasma technologies insofar as the gases or the mediums that become the interface with the surface of the material, they're being ionized, so you have ions, electrons, and other species that are bombarding the surface. Ultimately, with a variable chemistry plasma, however, you have a charge-neutral effect. This charge-neutral effect is a result of a balance between these different charged species so that there is a discharge, if you will, of existing charge from the surface of the material. These are all non-thermal plasmas. There's a lot of depth and discussion that we can go into further in terms of what these specifically are, but suffice it to say that the species that are contained within this discharge normally will raise the surface tension of the treated material no more than about 6 to 10 degrees Fahrenheit. Again, even though the electrons and the electronic discharges is much hotter. And as opposed to vacuum plasmas, variable chemistry gas phase plasmas in atmosphere have a very high density discharge. And so what you can expect is a very low dwell time relative to the exposure to the material surface to get a very high surface energy effect. Not to create a lot of confusion with regard to this type of a diagram, but if you focus your attention on the white square That we're representing as, for instance, an air plasma-based discharge. And this is an approach that allows me to talk to you a little bit about what the reaction mechanism is for these type of discharges. Again, within an air plasma, the medium is air, so we're talking about an ionization of M2 and O2 and water vapor in the form of H2O. After that reaction takes place, initially you have initiating radicals that come to bear just outside of the initial discharge mechanism. So then again, you have radicals such as atomic oxygen, nitrogen, OH groups, hydrogen groups that are all beginning their pathway to the surface of the material. Continued reaction ultimately generates gas phase products such as small amounts of ozone, the oxygen molecule associating and dissociating in air. You have nitrous oxide, nitrous acid, nitric acid, all of these functional groups that can play a key role in their small quantities of functionalizing a surface. If we follow this reaction pathway, again, to the surface of a polypropylene substrate, you can see that these discharges ultimately make their way through a boundary layer, and that boundary layer is typically an atomic surface layer at the material to the, or into the atomic layers of that material, and you see different types of functionalizing effects. In this case, we're representing the water vapor, the oxygen and the nitrogen in air, ultimately ionizing into those free radical groups, free radical species, making their way and attaching themselves through that free radical effect and that abstraction effect to the surface of the polypropylene. The depth of the treatment, we typically get asked this question, is typically around 8 to 10 angstroms in depth relative to the surface. Again, it does not need extremely deep implantation into the material to affect adhesion because, again, the objective here is surface adhesion. And so that is readily accomplished by this pathway. If we change the equation here and we look at the reaction pathway for a variable chemistry plasma, you can see that we introduce one particular type of chemistry, and that is a flame plasma that uses methane. And again, we call this a variable chemistry because you can actually change the type of hydrocarbon gas and yet still get a very functionalizing effect. In this case, again, the stoichiometric ratio of 10 parts air to 1 part gas allows us to introduce an oxygen molecule and a methane molecule, CH4. Ultimately, we get a penetration of the boundary layer and the same type of an effect relative to free radicals and attachments to the end chains of the molecular structure of the material. If we go to a gas-based or gas phase plasma, also a variable chemistry pathway exists. In this case, we're representing a plasma forming inert gas, helium in this case, with reactive components of oxygen and nitrogen in atmosphere. You can see that, again, the same type of depth of treatment, the same type of free radical effect takes place. But in this case, you're allowed the opportunity to change the surface chemistry relative to the chemistry of what's going to be applied to that surface. And so if we're working with the adhesion of a solvent-based paint, of course, there's an opportunity to change the gas chemistries to allow us to functionalize that surface and create covalent bonding with that solvent carrier. If we're working with a UV-based light curable type of an adherent, that could be, again, an adhesive or a coating or an ink or paint, we would want more amine functionality. And of course, that would be part of the equation that would be introduced. Wanted to show you some still frames of exactly what's going on. With every plasma treatment, we end up seeing a cleaning effect where we're removing low molecular weight organics. Ultimately, then, we can create an increase in surface area by the ionic bombardment of the surface, and then ultimately a change in the functionality of the material. So again, just to review all of these, it's cleaning, functionalizing, and increasing surface area. When we look at specific polymers, and again, we're going to use polypropylene as the example here, again, the objective here is to increase surface energy relative to time. With atmospheric systems, the time spent is fractions of a second. In this case, we're showing you an example of a vacuum plasma approach, which is a low-density discharge, moving a polypropylene surface from a hydrophobic surface characterization to a hydrophilic characterization. But you can see that the duration time is usually in a large amount of seconds to get up to a minimum amount of surface energy. Again, with an atmospheric plasma, that type of change is within milliseconds relative to the exposure time to these type of discharges. And yet the treatment effects can be the same. You can see in the left margin an untreated polypropylene structure under SEM, and then you can also see a plasma-treated polypropylene structure. And what you're seeing at that surface are small nodules. These are, again, small, low molecular weight nodules that make their appearance most typically with plasma treatments, usually flame plasma treatments at the surface. And of course, if you were to overtreat a polypropylene or any other type of material, increase in number, and ultimately you would lose contact with the native surface of the material, and that would allow you to create a delamination effect, which you certainly want to avoid. So understanding the power density requirement and the functionalizing requirement of the surface is key to a successful outcome. So again, just to ground everybody, untreated polypropylene is typically hydrophobic. It is also typically crystalline in nature. When you increase surface energy by some form of plasma treatment, you will create a form of functionalization at the surface and different types of hydrophilic groups. Those groups could be carbonyl, carboxyl, hydroxyl, amine, amino-carboxyl, and different types of combinations of such. But ultimately, once you've decided upon the type of chemistry that is required for the application that you are working with, you need to, again, add to that equation an energy density. And that is usually prescribed understanding the parameters that surround the cycle time of the process or the line speed of the process. Again, this approach of changing the surface of a material or the surface structure of a material with an air plasma, for instance, is all about extraction and hydrogen extraction, where we're removing or changing the chemistry that exists and substituting it by reactive oxygen species with oxygen atoms. And in this case, we're showing you the generation or the beginning process of generating proxy groups. No matter what is done, it's all about making sure that you achieve the right outcome relative to a specific surface over time. Now, as time goes on, if a material has been treated at extrusion or at the time of extrusion, usually you have a decrease in that surface energy relative to the extrusion level. Time, humidity, the level of humidity at the time of extrusion and during its exposure to humidity, different processing additives that are added to those type of materials. That could be anything from fillers to fatty acids. All of these can have an effect and ultimately a migration to the surface that can create some type of contamination. So again, in order to be able to achieve the right outcome at the time you are going to apply the next process, it's important to retreat or at least bring the surface energy and its chemistry up to the level it's required for successful converting. Different types of additives that are seen on different types of polypropylenes and polyethylenes, could be oleamides, racemides, ceramides, or sterets. Also, there's issues with regard to three-dimensional objects with the use of mold releases and their presence on the surface of molded materials. All these have to be dealt with and anticipated in a way and a method that allows you to successfully bond another material to the surface of the base substrate. Now I'd like to just compare these different types of plasmas so you understand why they're as effective as they can be. A plasma torch, again, a very high velocity discharge. It is a plasma. It's a very high plasma density in terms of the electrons within a set space, in this case cubic centimeters, and an oxygen atom density in terms of electrons per cubic centimeter. It's all because of the velocity of the discharge and its uniformity and its homogeneity that gives you these type of densities. In comparison, an air plasma or a corona discharge will have less electron density relative to the plasma itself, as well as less oxygen density. Why is that? Well, the reason is because we are not forcing any type of an airflow or a gas flow to the surface. In this case, we are reacting ambient air, mostly ambient air, at less than high velocity or less than the velocity of a plasma torch, and ultimately you have a reduced density. When we work with modifications of these type of discharges, these type of atmospheric discharges, such as a dielectric barrier discharge, they're going to be similar. The similar effect is because you have an anode and a cathode, and you're still reacting in the same less than plasma torch velocity of these type of gases. And of course, when you're in a low pressure glow discharge or a low pressure vacuum plasma, there's certainly no oxygen density and certainly a very low plasma density. That is why the dwell time is so high, and necessarily there's been a lot of movement from vacuum plasmas into inline continuous methods for productivity reasons alone. We look at RF atmospheric-based high-density discharges. You can see that there's an upstep in the plasma density as well as the oxygen atom density. And this density with oxygen atoms can actually be increased even further if oxygen is used as one of the reactive chemistries for this type of discharge. Now, what can be the effect of all these discharges on a surface? In this case, we're representing what's achievable with atmospheric plasmas in all their forms. And certainly what you can see here, whether it's a hydrocarbon or a fluorocarbon or an elastomer or a fluoroelastomer or some kind of engineered thermoplastic, all of these materials can be raised to a level of 72 millinewtons per meter or water wettability. Their contact angles can also be reduced dramatically. Is it necessary? No, of course not. Is it advisable in every case? Also, of course not. What is important to note here is that there is capacity to get there if there is a need to be there. But in most cases, and Enercon included, there would never be a recommendation to achieve these specific type of levels without understanding that the interface with that surface demanded that level of treatment. And so usually our prescriptions and the industry's prescriptions are significantly less because the investment and the economies of such really demand that type of appropriate level of treatment. I want to talk briefly about composites. Really, composites don't get much attention, but it is an important part of the equation today in terms of the use of materials and their specific types of properties. When we look at and deal with composites, we see a lot of composites in the form of, for instance, decking, composites in terms of wood polymer decking materials. Just as a metric for you, the wood plastic composites gain in market share in the United States has moved from 2.4% to a level of approximately 18.6% over time. And this metric as of 2009, and the projected effect up to 2014. It's quite a step change, and as we see more of these materials, we have to take note of the fact that it's the matrices that make up these materials that are the main determinant of what the ultimate composite surface energy is. So even though we recognize that, for instance, a carbon fiber reinforcement inside of a peak or polyether ether ketone matrix may be heavily populated with these carbon fibers, it is primarily the matrix material that will determine how we functionalize the surface of the material for adhesion to another composite or another virgin material. The same thing applies with these other materials, most notably Kevlar. Has a very low surface tension at 27 dynes per centimeter, but the epoxy matrix is the determinant of how it's going to get functionalized. Whether it's a composite or whether it's a virgin material, there are some key adhesion impediments that everyone deals with here at Enercon and among our competitors in the industry, and that is low surface tension, also the presence of additives, the migration of additives that are there for processing but get in the way of ensuring that surface energy and the functionality is there for adhesion. Certainly with three-dimensional injection molded pieces, you have mold release interference. There's also this issue of temperature. If a material has a specifically high temperature at or during processing or a specific low temperature during processing, that can affect the adhesion of specific types of adhesives or coatings or inks or paints. That is a key consideration relative to acclimation, and it really goes unnoticed many times in industry. UV light, in the presence of UV light, not just for energy curables, of course, but for the adhesion of a surface is important, because that photonic interface with a surface can actually change the functionality of that surface. Also, with regard to a specific type of material and its adhesion with another material, the mechanical stresses that both materials are exposed to will affect certainly the level of adhesion and how you need to plan for treatment of those materials. And then finally, the design and fabrication of the materials. A lot of this stress, a lot of these environmental factors and exposures need to be incorporated into the design, form, and function process. So designing and fabricating appropriately will minimize the effect of these stresses on adhesion. But when we boil it all down, it really comes down to the top three: low surface tension, additives, and mold release agents that are the biggest issue with regard to achieving and maintaining long-term adhesion. There are other types of anomalies that can interfere with adhesion. We won't deal with them in great depth here, but we will tell you in terms of advice that when we look at the different types of plasmas that are very functional for removing organics, and oxygen content plays a key role in ensuring adhesion. Also, we find that RF energy, RF system designs are important in creating the right type of change at the surface of a material. We want to get to a level where we are interfacing atomic oxygen to a surface, and that is an important element, especially with air plasmas. When air plasmas generate the type of discharge we're looking for, we get a byproduct, and this is common also with plain plasmas and variable chemistry plasmas, of water vapor, small amounts of parts per million of water vapor, CO and CO2, very small parts per million. With variable chemistry plasmas, we get most of the inert gases that are part of the process, but of course, because they're inert, they're not critical exhausts. But nonetheless, all of this is carried away. Much of it is very benign and typically do not require any type of destruction systems that will add to the cost of an investment in these technologies. As promised, I wanted to get to you the recommendations that we have for specific types of materials. Of course, this presentation will be made available to you, so you don't have to copy this all down, but we wanted to relate to you different types of thermoplastics and thermosets. A lot of these materials are very difficult to treat. Some are very crystalline, some are designed to be very heat resistant, some have inherent toughness to them, chemical resistance. All of these features and properties will affect the type of atmospheric plasma that's applied to their surface. And so we give you some key characteristics of each of these materials that have an effect on how successful you can be in treating, and we identify the specific type of treatment technique that we think and have found over our experience have been best in functionalizing these materials. All right, at this point, what we'd like to do is move to a live broadcast segment of this presentation. And so what that means is that I am going to turn this over to literally a camera, and that camera will be focused specifically on three different types of technologies. One is going to be represented by our blown arc technology. Another will be a demonstration of blown ion technology. And a third one will be variable chemistry plasma technology along with flame technology. And so the approach here is to give you some type of real-time, and I think this is rarely done, but some real-time exposure to the type of discharges that have a very profound effect on the material. So at this point, I'm trusting that you're seeing what I'm seeing, and that first focused discharge is a blown arc design. It is the cylindrical head design that you see in the foreground. And so here we go with that discharge. The second discharge is for a blown ion technology. Blown ion technology is all about streaming simply ions to the surface of a material in a very focused manner. The third technology is variable chemistry plasma. And in this technology, you incorporate not only the use of air, but different types of gas chemistries that can again be discharged to a specific type of surface. All right, so those are the three primary type of discharges that use some combination of air. And at this point, I'm going to show you a treatment using the blown ion technology. And we'll represent that on a piece of polymer material here. And as we focus down with some dye solutions on a sterile cotton swab, you can see the wettability of that particular dye solution right down the middle of what is a very hydrophobic material. So again, a very successful outcome. Now this type of an outcome is really dependent not only on the type of technology and the type of material that's used, but also the velocity of the discharge and also the gapping between the head of the electrode itself and the material. Okay? All right. We're also now going to switch over to another technology, and this is our flame technology. This technology is going to be using methane gas in combination with air, 10 parts air to 1 part methane gas. And that technology is calibrated to allow us to focus the right amount of energy relative to a specific type of surface. So we have ignition, and we see the profile of a flame discharge out of a typical burner assembly. Now that burner assembly, as you can see, will profile inner cones and an outer cone. The inner cones that you see, those greenish blue cones on the inside of the flame, are the primary treatment zone cones. And you want to interface the surface of a material with the tips of those inner cones in order to affect the highest level of oxidation as well as the highest level of surface energy. The secondary treatment zone is there to allow us to treat, ionically and electronically treat the surface, but not to the highest degree. But the profile of that discharge also allows us to encompass a large profile, a large contour of material. Okay? All right. So that demonstrates our technology relative to air plasmas, flame plasmas, and variable chemistry plasmas. Now, not only has our atmospheric plasma technology been anchored by these type of three-dimensional devices that you see in the corners of this particular slide, but you can also see in the internal aspects of this slide the different configurations that are available for different types of materials. These materials can range from, again, sheet materials to roll-to-roll web materials. It could be roll-to-roll one-side treatment, roll-to-roll two-side treatment. It could also be the entrainment of filaments and yarns through a specific type of discharge. It could be the conveyance of textiles, could be the conveyance of foils or metallized films. A wide range of materials are conveyed through different types of designs. Everything is usually designed to the process that is most appropriate for the conveyance of these materials, meaning that these designs are made relative to the process and the customer's line. So again, that's some insight into the different types of physical representations of these technologies. Besides, for instance, the automotive industry, which is really picking up strong, and the confidence index I looked at just recently is quite high. The latest statistic that I have, for instance, on the auto supplier confidence index for North America is that it's up to about 70.5. Not only is that quite high, but we're seeing the same type of confidence index in the electronic industry and also in the medical industry. Other industries that are more complex, that are requiring even more elaborate methods of surface modification, include the graphics and display market, the OLED market, the electronics and electronic communication market, including RFID tags, the healthcare market in terms of medical Tyveks and medical type of textiles, the solar industry relative to not only encapsulation layers and back sheets and front sheets, but also on the three-dimensional side relative to junction boxes and affecting the adhesion of potting adhesives. Also the cleaning of glass and glass structures to make sure that all of these modules, whether they're rigid or flexible, have hermetically sealed or very tightly sealed structures to avoid any ingress from any type of environmental challenges. There's also the demands of safety and security, polymer banknotes, where holograms are required, or specific types of inks or coatings, or reflective or refractive properties, all come into play and require different types of adhesions, including laminations. In the transportation industry, when it comes to lithium-ion batteries or other types of structures that use combinations of foils and separator materials. In manufacturing and industry, where it could run the gamut from textiles used for diapers to filtration media. We see the same thing in home and leisure with regard to not only filtration media but also other types of textile structures. There's a wide range of properties that need to be maintained for all of these base materials, and yet they need to be changed functionally on the surface to allow them to not only be graphically changed but also to change their functional performance relative to time and relative to the environment that they're in. So I'd like to give you some concluding remarks. The first one would be that all of these technologies really are quite environmentally friendly. We talked about the byproducts of the processes are very inert and very non-threatening, non-polluting, very green technologies. They don't consume a lot of energy. In fact, they consume very little energy in terms of operating costs. No drying time required. Again, no waste disposal issues. In fact, if there are applications that involve solvents and other types of surfactants that are used to clean surfaces, a lot of those type of processes are being substituted with atmospheric dry cleaning and functionalizing processes. When it comes to your operator and operators that use these technologies, there typically is, again, no type of toxic gases, no type of radiation, no type of exposure to surfactants and chemicals that are going to be harmful to the operator. Of course, some of these are high voltage discharges, so of course the appropriate type of guarding is necessary in any type of process to protect employees and operators, but beyond that, there is nothing else that is threatening. All of these system designs, all of these types of equipment and methods for changing surfaces are fully controllable, all electronic. When it comes to the variable chemistry systems, all of the gas flow controls are mass flow control operated digitally. A lot of these systems will provide quality control information in terms of data logging, historical records relative to when and how surfaces were modified. Depending on the type of process that's used, whether it's air plasma or flame plasma or variable chemistry type of plasma technology, there will be typically, number one, a high degree of surface activation, and depending again on the type of material and the type of interference at the material surface, long shelf life. And we can characterize to you that type of shelf life depending on the type of material if a specific type of application is presented. Also important to note that even though these are high density discharges to surfaces, there is absolutely no change in the surface morphology or the bulk properties of these materials. And so there's nothing that's visual relative to any type of surface change that's taking place. And then again, no matter what the type of geometry is, whether it's a flat sheet, whether it's a contoured or complex geometry, or whether it is a roll-to-roll web, all of these substrates can be changed in very quick order, very fast order from a surface modification standpoint with the right type of technology. As mentioned earlier at the outset of this program, just to help you as a resource, Intercon has a book that's published. It's called Plastic Surface Modification. It's available on Amazon.com in the United States, in the UK, and out of Europe, Germany, and also in Asia. We encourage you to look at that particular book and see if it provides the type of resource information you need. And at this point, we would like to send it back to the Plastics News team and open it up for questions and answers. Okay. All right, I can take hold of this. It's not a problem. I'll be glad to move through some of the questions. There are quite a few attendees, so I'm not going to be able to get through all of the questions by any means, but I will use the available time that we have, which is about approximately 10 minutes, to talk through a lot of these questions. So I'll take it from here. One of the questions has to do with what the type of plasma or source of plasma is required. Oops, I think we've just, hold on a second. Let me get to that right question. There we go. Thank you. Relative to the type of technology that you use, how long can you plasma treat a substrate without degrading it? That's a very good question that was just recently asked, and I'll answer that question again. It depends on the material, and it depends on the treating device itself, and that will determine the approximate amount of dwell time. But it is typical that you can get, again, certainly up to at least a second of dwell time without much surface degradation at all, if any surface degradation. Usually, again, all of these processes will treat in fractions of a second. Another question that's been asked here, how does this process work with polyester and solvent-based materials? Very easily, actually. Polyester is actually one of the more easily treated materials. It is typically quite polar. Solvent-based materials that may be applied to polyesters, again, are most readily wetted out on these types of materials. So it's very easy to functionalize and prepare them for solvent-based adhesion. Another question, how does a static eliminator affect surface energy? Great question. When you apply a surface treatment relative to corona, flame, atmospheric plasma, whatever it is, and you are applying that to a material prior to static elimination, the effect on the surface and effect on the surface treatment is negligible at all. What is important to note, however, is that the remaining static that is in a material can change the reading of surface energy, because that static will affect the dyeing liquid, the liquid that is actually wetting to the surface to be used to read the surface. So it's important to note that even though you have positive and negative ions being sent to the surface in the form of a static eliminator, or if you're using ionized air to reduce static electricity, it's always best to have that done after treatment, but prior to measuring a surface and its energy. Again, it doesn't affect the surface energy per se after treatment, but it does affect the reading of the surface energy. Okay, another question that's been asked, and I'll just answer this one up front because it was asked once before, and I tried to address it at the beginning. How do we get a copy of the presentation? That presentation will be available to you on the Plastics News website about 24 hours from now. So we hope everyone will have a chance to access that by Friday. Next question, and we have time for a few more questions here. The question is, how does surface energy of nylon or polyamide 6 and nylon 12 compare to? Normally, polyamides have a slightly higher surface energy than polyethylene in its native state. However, that being said, we do say and we do see that the treatment of polyamides is just slightly more difficult, not to a great extent, but slightly more difficult than it is for treating polyethylene. What can make polyethylene a little more difficult to treat, again, is its exposure to or its integration with different types of additives. And, of course, whether it is a high-density polyethylene, a low-density polyethylene, or, let's say, a ultra-high molecular weight polyethylene. So all of these structures on how easily these materials are treated. I see some related questions in that regard. Let me also deal with a question with regard to this one. How long can you plasma treat Oops, that's the same question. I'm sorry. Questions are coming in and they're queuing up and showing themselves in different positions, so I apologize for that. Another question here is, how many times can you apply corona treatment to a polyester film? That is easily answered. You can actually corona treat a polyester film and then corona treat on top of it. The guard against that, however, is if the polyester film has been treated to a very high level, it's already near a state where it's probably accumulated these low molecular weight organics that we had talked about earlier. So applying additional corona treatment to that type of a surface condition can actually create a negative effect and possible delamination. If the polyester film was treated to an appropriate level and you wanted to apply a slightly higher level of corona treatment or bump treatment to it, that is very acceptable and very easily done. Another question here, how thick, and I'm just going to look at the wording here. I think the wording is, now the question's just shifted on me, but how thick can the plasma ion penetrate the surface? I think what that is meant to ask is how deeply will an ion that is delivered or bombarding the surface penetrate the surface of the material. Again, typically we see that, again, no more than 10 angstroms in depth. There are other types of plasma devices that will create deeper implantations, but those are usually done for a different reason. Those are devices that, such as, again, ion implantation devices, which have a different purpose and an objective relative to changing a surface structure. And so in the realm of plasma surface treatment, ionic bombardment does not penetrate beyond that 10 angstrom level. Another question relates to how to create primary amine groups on the surface using plasma. One of the ways to do that is to use an atmospheric plasma that utilizes ammonia. Secondary amines can be applied by virtue or by use of nitrogen or nitrogen-based chemistry. You can also use combinations of or premixtures of nitrogen with hydrogen. The one caveat there is that you've got to make sure that the mixture percentage is below the explosive limit with combinations of hydrogen. We have that experience. We have those type of gas mixtures here, and so we have the ability to talk to those type of issues and prescribe the right type of adhesions for those. Let me just ask or answer, I should say, one other question here before time is over. The question is asked, how would plasma treatment increase the surface energy of a metal substrate like aluminum or stainless steel? Well, what we typically see with aluminum or aluminium and stainless steel, we see it also with titanium, we see it with aluminum, we see it with copper, we see it with the different types of alloys, that these type of materials will have processing rolling oils on them. Sometimes they're clean to different class levels. Other times they're pretty raw in terms of their state of contamination. But in all cases, and we're doing those types of tests this week as well, plasma treatment increases surface energy by volatilizing and vaporizing these organic contaminations on the surface. The species are of a size and impact of the surface that allow cleaning of the fine grains of these materials, these metals, ultimately raising the surface energy. And if many of you don't know that are online, these starting surface energies for these metals are usually in the 30s and 40s in terms of millinewtons per meter. In their purest state, these metals can have surface energies as high as 1 to 2,000 millinewtons per meter. So there's quite a range or an opportunity to clean these metal substrates, and plasmas do a great job of doing that. Before I wrap up, I did, and I'm going to segue back to the Plastics News team, but before we wrap up, we'd like to remind everybody that we do have the capability of providing inline continuous trials at Enercon on two different atmospheric plasma labs. We have lab lines that convey roll materials as well as sheet materials. And we have a separate atmospheric plasma lab with all these technologies that will convey three-dimensional objects for treatment as well. So if you have the opportunity to seize and utilize those technologies at any point, we're glad to do those for you on an as-needed basis. The second thing I'd like to talk about real quickly is that, again, all of these questions that have been asked, and there are, looks like there's hundreds of them. I'm glad to be able to answer them all in due time, and I will tackle them immediately after this webinar. But we're going to make a very concerted attempt to get back to you on a very timely basis offline. So thank you for the many questions, and we look forward to answering them. And back to Plastics News.
Okay, thank you, Rory. Certainly a lot of interest. There's a ton of questions, as you rightly noted, and we apologize for not being able to get to more, but I'm sure that Rory and his team will follow up as quickly as they can. And meantime, we just want to thank both Rory and Enercon for sponsoring this webinar, and as he has reminded you a little while ago, I'll repeat it. Today's presentation, as well as Rory's slides, will be available in about 24 hours time at www.plasticsnews.com/webinars. So with that, it concludes today's webcast, and we look forward to perhaps seeing you back here again. Thanks very much.